Ora si registrerà la conferenza.
My name is Thomas Hakala, and I'm a co-founder of Convion. Today, in this fourth and final part of a series of DEMOSOFC mini webinars, we'll be discussing about economic aspects of the DEMOSOFC plant and possible replications of similar concept elsewhere. We've structured the presentation so that I will first talk a little bit about the application and the DEMOSOFC project, and as always we have to consider alternatives to do the same job or similar job, and then discuss how they differ from each other economically. I will touch the issue of cost projections of solid oxide fuel cells and fuel cell systems. It's an important part of it. Obviously, this is still an emerging technology and not fully commercialized, and therefore the cost levels today are far from where we foresee them to go. I will show some thoughts of how in this kind of application different technologies compare, and then I'll switch back to Gwemi, who will present her studies on pathways to commercialization, and then after that we can conclude and have a questions and answers session. During the presentation, please use the chat to write questions, and then we'll go through them at the end and not interrupt the presentation all the time, because it's there are quite a lot of people here. Okay, a little bit of repetition. Some of you have been in these webinars earlier, some of you haven't. At the very heart of the DEMOSOFC project is the idea of energy autonomous or partly autonomous wastewater treatment, and how solid oxide fuel cell technology plays a role in this concept. Curiously, well, wastewater treatment first of all is a very universal application. It's surprisingly similar in every city. The basic processes are similar. There are some choices you can make, but the biggest difference is usually scale. Curiously, wastewater contains enough of embedded energy for its own treatment. It's a fairly significant municipal energy consumer as of today, but it has potential of being energy neutral or even a net producer. Majority of wastewater treatment facilities are quite small, serving smallish communities, and therefore the entering load for biogas production is not sufficient to make power and heat production with conventional technology feasible, and therefore penetration of these technologies is quite low in small and medium scale. Solid oxide fuel cell technology has the highest efficiency of all technologies, and regardless of scale, and therefore it has some interesting promise to this along with many other applications. So this in very rough terms, the concept of DEMOSOFC. We have an existing medium-sized wastewater treatment facility with an entering load of approximately 180,000 population equivalent. There is anaerobic digestion process that produces biogas out of the sludge, the sewage sludge, and out of that gas we can produce electricity by solid oxide fuel cells. The facility also has a boiler that can supplement the thermal needs by burning either biogas or natural gas. In a full embodiment of the concept, this fuel cell installation would have produced 174 kilowatt electrical power behind the meter. It would all be consumed by the facility and cover basically 100% of the normal thermal loads. The promise is superior efficiency and an ability to offset power that would otherwise get purchased from the grid. Fairly infrequent maintenance breaks and well-matched heat output with continuous thermal loads required by the digestion process, and on top of that, zero local emissions. If we consider this kind of facility and what can be done with that biogas, it's a medium-sized, approximately 80 normal cubic meters per hour biogas output, but there are annual variations. It's continuous. There's constant demand of power and heat, but variations in those loads around the year and around the day. In this area, energy overall is relatively costly, and particularly electricity, maybe higher than European average. And then, as mentioned, there's a boiler available for producing heat independent from other means of using that gas. The fuel cell installation, as illustrated on top, requires fairly stringent gas cleaning. It provides the highest efficiency, yet sufficient thermal efficiency, highest electrical efficiency and sufficient thermal efficiency, but the investment required is clearly, well, particularly today, but also it will remain higher than the engines for quite a while. And this is new technology. It has some concerns, of course, and sort of teething issues. The obvious and quite common solution would be a piston engine, or in some cases a microturbine. Both of them would have a lower electrical efficiency, more frequent maintenance, but this is very well-known technology and can be loaded dynamically. For this application, it produces more than enough of heat, but electricity would be, out of the same amount of gas, would be lower. Then an alternative that is not necessarily applicable in this scale is a biomethane upgrading. In bigger plants, it's an obvious choice, and it is highly subsidized, producing a way of producing vehicle fuel. But typically, both the capex and opex make it attractive without particularly generous subsidies in megawatt scales. Also, the facility itself, the wastewater treatment, which is the sort of primary function, it requires both electrical and thermal energy, and then it would no longer be self-sufficient if all this gas would be used for other purposes. It's a very kind of condensed slide about how to compare different technologies, like apples to apples. An internal combustion engine is the obvious choice. For example, in Germany, you see thousands of smallish biogas engines. There are plenty, and the variety of different sizes is plentiful. Taken from actually a German CHP genset database, I plotted an investment cost here. Everyone can see that it's dependent on the power output, but it is very low compared to if you know anything about fuel cells. It's still quite low. Also, the efficiency on the right-hand side is dependent on the output. and sort of intuitively you can already tell that the very low end is the least attractive area, where the investment cost, relative specific investment cost, is highest, and yet the efficiency is lowest, and the specific cost of maintenance also becomes higher at the low end, because it's basically the same cost of maintaining a bigger engine than a smaller one. It's an affordable solution, and if you think of fuel as free, cost of unit of electricity generated is low. But if you think of a facility like a wastewater treatment plant that requires more than, well, currently more than the energy that can be produced on site. If you use an inefficient technology like piston engines or microturbines here, you have to buy more electricity out of the grid. And in both of the original DEMOSOFC concept as well as a potential alternative engine concept, there would be sufficiently heat for the process, and then the comparison is between electricity. Here on the right hand side, this is a very quick comparison of quite arbitrary point of 4,500 euro per kilowatt investment cost of SOFC. We're not here now, but it's not that far in the future either. Compared with the 100 kilowatt ICE, like a piston engine, if you take the values from this database, the fundamental levelized cost of electricity generated by this unit, if fuel is free, is very low. But if you then think that you should produce the same amount, so you have to supplement by grid electricity to produce this, or deliver the same amount of electricity to the system as the fuel cell system would do, then it turns the situation the other way around. The supplemental electricity from grid at the cost of 15.74 cents per kilowatt hour will actually make it more costly. So depending on how you sort of define the system boundary, which feasibility you evaluate, you can make an engine look like an interesting application, or an interesting investment, attractive investment with a positive ROI. But in the end, on a systemic level, it may not be the cost optimal. Obviously, there are other considerations such as maturity of the technology and dynamic aspects and so forth. But this is just a simple illustration of why in this kind of environment where there's an opportunity fuel, which availability is limited, it's a finite amount of gas, you have to look at the entire picture and not just the unit within one box. Then how do we get to the 4,500 and further? Of course, we clearly foresee cost competitiveness with piston engines, microturbines, and this kind of conventional technologies. Unfortunately, at least for all the competitors sitting in the audience, I cannot share with you our internal stack or system cost data, but instead I wanted to show you data that I sort of collected or put together from public sources. On the right hand side is the fuel cell stack. In our case, in our power range and with our technology, the entire cost of a system is practically 50-50 fuel cell stacks and then the system. And stack, therefore, it's the most costly, the costliest item in the system, and it dominates the cost in the future as well, and therefore it's very important. The data is collected from several sources, actually, from Roland Berger's study. This was like an industry-wide questionnaire or query, where companies operating in this field would share their views of the future, and including cost of stack. And I have just normalized it so that every stack cost is normalized per kilowatt net, and independent of the system size or stack size. And the rest of the points are from these Battelle studies, which are sort of educated guesses of where the cost in mass manufacturing can land. They're very widely investigated, but not based on actual production, but based on what it could be. And in some cases, they are a little bit optimistic, but the sort of different sources create a little bit of scatter in the plot, but curiously enough, they all gravitate towards approximately 500 euros per kilowatt net. This, so in gross, it's more, it's less, but they gravitate towards this same level. And that kind of, if the future cost is 50-50, then that kind of gives you an indication of where in very big volumes the cost could be. Of course, the system cost then, if you look at the plot on the left-hand side, depends on system size and system concept, stack size, and many other factors, how aggressively those stacks are loaded, for example. But this gives you an indication of both the annual production volume, as well as the effect of production volume on the cost, as well as system size. Obviously, the cells themselves are modular, but on the system side, which represents about half of the cost, there are things where bigger is more affordable relatively. And here you see that from very small scale systems to 250 kilowatt systems, there's quite a dramatic drop in euros in specific investment costs. I would say that the shape of the curves is correct, and these figures are indicative, but maybe a little bit optimistic, particularly if you look at these volume points during the scale-up phase. These are representing. Excuse me? Excuse me. Okay. Does someone want to ask something? I hear some noise. Can you please mute the microphone? I will quickly switch to.
I think I muted him, so you can continue.
Okay. So yeah, the scale and volume drive the cost reduction, and we see that it doesn't really take so many megawatts per year to bring down the cost very dramatically. The other thing that drives cost reduction is simplicity. That is the sort of architectural, conceptual innovation and product industrialization. These are relative figures. The year 2012 was our Wärtsilä background level as a relative 100%, and we've taken some steps down this path. First, by process simplification, reducing number of functional components and associated instrumentation very much, and being able to bring down volume of the system very significantly. Then there are further component optimizations. So these are steps along the industrialization corridor or path. Component optimizations to bring down balance of plant cost, and then further integration and manufacturing optimization, where we are sort of entering this phase now, or we have a design ready where all figures of merit have reduced quite dramatically from the beginning level. Number of functional components nearly 70%, instrumentation over 70%, weight to power ratio almost 90%, and volume to power ratio more than 70%, and very radical improvement in the cost potential of the balance of plant in serial manufacturing. This is not today's figure because the volumes are not there, but it shows that this is an important area, integration and industrialization of manufacturing. I will now switch to Gbemi. She will discuss about the pathways to commercialization and particularly look at also this biogas and industrial biogas applications. Shall I think I will have to stop sharing and
and I will start sharing. Okay, thanks, Thomas. I hope everyone can see my screen.
Not yet.
Yes. Do I have permission to share my screen?
You have on the account where you are talking, but there are two. If you want, I can also allow the other.
It's the other account, please, not the one I'm talking.
Okay,
yeah.
perfect.
Thank you.
Okay, now you should be able.
Yeah.
Perfect. We can see the screen now.
Okay, perfect. All right, so thanks everyone. I will just continue, just following on from what Thomas just presented. I'll be showing various pathways to commercialize the SOFC in European wastewater treatment plants. It's just showing how we can get from today's high capital cost to a point where the SOFC is economically viable, that is cheaper than the business as usual way of providing energy on a plant, or cheaper than its competitor. And we'll see how business models, policies, and the market can take us there. So the question in synthesizing a pathway to commercialize any new technology that it's cleaner, more efficient, but also more expensive than the competitor is, how do we exploit the size of a market to deliver demand and associated manufacturing volumes that can bring about, cost reduction and take us to the point of commercialization. So to answer this question, we've developed like a market potential analysis for the SOFC. It builds on the thermodynamic analysis of the technology. It builds on the optimization design to integrate the technology into a plant. It builds on the techno-economic assessment of the SOFC in each plant to the techno-economic assessment of the SOFC in various plants that make up the market. What we want to be able to measure is the market share of the SOFC. That is, if you consider all wastewater treatment plants in Europe, which of these plants is integrating the SOFC economically viable, and how can we use that to start cost reduction and also trigger cost reduction, and sustain it up until the point where the SOFC can be driven purely by market forces. For the demo SOFC case study, the market we're considering is wastewater treatment plants in Europe, where it's economically viable to install an anaerobic digester. We've identified about 6,000 plants where today you could possibly install the SOFC. Now, each of these plants in each of these member states will occupy a fraction of the market. Now, the market, it's not limited to this. The market could be a global market, but for demo SOFC, we're looking at European wastewater treatment plants. An optimization-based design of each of these plans shows that the ideal demand for the SOFC is about 13,000 units. So the SOFC is of course not economically viable in any of these plans, but an ideal demand is that. So how can we exploit this ideal demand to bring about cost reduction? As you've seen in Thomas' slides, there is a relationship between increase in manufacturing volumes and the potential to reduce cost. And this is from learning by doing, this is from improving the manufacturing process. This data again was taken from public sources. So if today the SOFC cost is about 16,000 euros per kilowatt, the objective of the market potential analysis is to show how are we going to exploit these 6,000 plans and the associated demand to create a manufacturing volume that can trigger cost reduction and sustain it until the point where the SOFC is economically viable. Now, based on this graph, we can come up with different categories of cost, the very high cost today to the target cost sometime in the future. Now, a good technology does not need to get to the target cost. As you've seen in Thomas' slides, for a capital cost of about 4,500 euro per kilowatt, the SOFC levelized cost of electricity was lower than the competitor. So in sense, a good technology does not need to get to the target. It's what do we need to get to that point when the technology is economically viable. So today, for example, if you sell 100 units, then you can get to about 8,300 cost reduction and so on and so forth. So what we see is basically we need to sell 10,000 units to get to the target cost reduction. So how can we exploit this demand of 13,000 units to create pathways to commercialize this technology? The demand is there, but the SOFC is not economically viable in all the plants. Therefore, we need aids or routes to the market. There are various routes for a technology to get into the market. It could be market-driven, which is purely by energy prices. And for CHP technology, you're looking at the spark spread. A technology could also be driven by policy interventions. So the SOFC has been demonstrated. What we want are demand-pull policies. For example, the feed-in tariff, feed-in premium, tax mechanisms, and quota systems. Most of the plans we've identified in the first slide are eligible for some of these policies. What we want to see is what's the impact of these policies in commercializing the SOFC. Another route to the market is business model innovation. This is particularly important for technologies that are cleaner, more efficient, but more expensive. So how do we use, so the SOFC being more efficient than its competitor means that there are savings in operating costs every year, as we've seen in the DEMOSOFC plans. So how do we exploit these savings in operating costs to pay for the technology costs? This is changing the way the SOFC is purchased. So instead of paying upfront in year one, is it possible to spread the cost for the lifetime of the technology? And how does this increase its market share? The next aspect is on incentivizing business models. Now, the common practice is to have policy interventions for technologies. So in the case of the FIT, the feed-in tariff, a price is given for electricity generated from clean energy vectors like biogas. What if we have policy interventions to encourage business model innovation? So for example, if a particular plant agrees to plow back all the operational savings in using this technology for its lifetime, then it should be eligible to receive some form of tariff from the government. What we've seen in this study is, whereas you need a high FIT for the SOFC, as high as 15p per kilowatt hour, if you decide to policize or use policy interventions for the business models, you need a low feed-in tariff as low as 2p per kilowatt hour to make an impact. So that's something for policymakers to think about. And then finally, is combined routes, which is just a combination of the above four. So we'll show how these routes to the market can be used to synthesize pathways to commercialization. The first pathway is the natural pathway. Of course, this will be driven purely by market forces, existing policy instruments, so policy instruments that the plans are eligible for today, and also business models. But in this case, the business models will be quantified at a high discount rate. 9% is selected as a high discount rate. Of course, this would discourage investors, but if a high discount rate is sufficient to trigger cost reduction or to introduce the SOFC into the market, then it's good enough. And then we have the accelerated pathway. For new technologies, an accelerated pathway might be required because existing policy instruments might not be sufficient. So the accelerated pathway will take into account simulating a higher value policy instrument. So if the FIT today in a plant in Hungary is offered at 19p per kilowatt hour, the accelerated pathway will assume that this FIT can be offered at a higher value, maybe 25p per kilowatt hour, and will be used to measure the impact on the market. So that's what the accelerated pathway takes into account higher value policy instruments, the business model quantified at a low discount rate, for example, 3.5%, and the impact of incentivizing business models and combined routes. Now, what does an output of the market potential analysis look like? We've got these routes to the market, which could be market driven or incentives or business models. We want to show how increasing the market share, increasing the occupation, the adoption of the SOFC in the market can bring about a reduction in its capital cost by exploiting the size of the market. So this graph was from the first slide, the ideal SOFC demand in the wastewater treatment plants we considered. So specifically, we want to say, what is the impact of incentives in creating a market share today? So the market share, so if, for example, incentives are implemented in some of these plans, it's possible that out of the 6,000 plans, 4 plans are economically viable. Therefore, the market share will be about 4 divided by total number of plans. Then how much demand can we generate today by implementing the incentives, and how does that result in cost reduction up until the point where the SOFC is driven without any interventions? At that point, we say the technology is economically viable. Now, the good thing is a promising technology only needs to occupy a fraction of the market. Our goal is not 100% of the market. The end goal is just a market share to ensure that the technology is driven purely by market forces. Again, the goal is not 100% market share, but just a market share that can trigger and sustain cost reduction up until the point where the SOFC is economically viable. Now, the natural pathways, results from the natural pathway to commercialization is shown in this slide. What we see is the only incentive that can make an impact today is the feed-in tariff that is offered in Hungary. So you can see the graph to the right showing the SOFC demand in Hungary as a result of the feed-in tariff. It's currently offered for 25 years. And the market share is very low, is 0.6%. However, this can bring about, due to the associated demand and increase in manufacturing volumes, you can have about 38% cost reduction. The challenge with the natural pathway is the cost reduction, even though it triggers the cost reduction from the very high cost today to some 38% today, it cannot sustain cost reduction until the SOFC is driven by market forces. Our analysis show that the SOFC is driven by market forces if you can reduce the cost to about 4,500 euro per kilowatt, which is again very similar to Thomas' analysis. So how do we get from this point to this point today? So the natural pathway, of course, cannot take us there. Incentives today in all European countries can only give us 38% cost reduction. Again, this is good for the technology. This is also good for the manufacturer. But ideally, we want to be able to trigger cost reduction and sustain it. If you look at the accelerated pathway, that takes into account a higher value incentives, business model innovation, as well as incentivized business model, what we see is today, for the higher capital cost, it's possible to trigger cost reduction with the associated SOFC demand and sustain it up onto the point where the SOFC is market driven and it's even possible to occupy over 90% of the market if you incentivize business models today. Even again, what we see in this graph is higher value incentives, the green line, are still not sufficient to sustain cost reduction up until the point the technology is market driven. So if we want to accelerate adoption of the SOFC in wastewater treatment plants in Europe, we need to think about policies in addition to innovations in business models. And this is where I'll bring my presentation to a close. Thomas?
Yes.
Yeah, I'm sure. I'm done.
Okay, good. If you stop sharing, I can put on the conclusion slide.
Yeah.
Hang on.
I am assigning you the role to share the screen.
Thank you.
Now you should be able to do.
Okay, excellent. Thank you. Okay, it was a very concise treatment of a lot of thinking that we've done over the years. I think this project has provided us a sort of breeding ground for ideas, and we've managed to also showcase the technology. As it is today, it is a technological demonstration, but we know that the byproduct biogas from wastewater treatment processes can make these facilities self-sufficient with energy if the conversion efficiency is high enough, and that is possible by solid oxide fuel cell technology. We know that the output quite well matches with the demands, and there's always a way of meeting the varying thermal needs by a boiler. As I wanted to highlight, you have to take a systemic look of the entire facility to see when the internally produced electricity is actually cost optimal, and when not, even though an individual piece of equipment might look attractive investment. We know, and we've shown how the solid oxide fuel cell, both the cell stacks and the systems volume is the cost is very much dependent on volume of production. It is, however, worth noticing that these volumes that we mentioned, 10 megawatt per year or 50 megawatt per year, it's a very low volume in the world of energy. If you think of any other generators, these are not big figures. It is actually quite surprising how soon we can reach the levels that are already bankable in certain markets. There was Bemi mentioned incentives as a way of sort of opening the path to the market. Biogas receives very different treatment in different countries. I mean, politically different treatment, and in some countries these incentives are in place and they can sort of pave the way and generate the early market and create the references that are needed for actually building a business based on this kind of applications. Market forces can drive clean energy industry going forward, and I think we see a lot of synergies with other clean energy technologies. So they are more than competing with each other, they are actually complementing each other. We see distributed structure overall in energy systems. In order to reach the levels of volume that are needed for the commercial price reduction and sort of get the ball rolling or running, we only need to occupy a fraction of the market, and biogas or wastewater or waste biogas is just one sector, and there are so many other sectors interesting for this technology. And yes, the level of economical viability is not that far, particularly with bigger systems that are building blocks for industrial scale systems. The level where these become interesting as investments is not far. I would say the biggest issue is actually the very limited number of references, because then that creates the credibility. It's not so much the cost that is limiting, but the lack of long-term data. And like Bemi said, we need simultaneous innovations in policy and business models, well, together with technology, to trigger cost reductions for this technology. We can close the presentation here. I see that we've already received some questions through the chat, and Marta, maybe you can, there's another channel for questions. If you see any questions, we can take them through you. But if I start from the questions in the chat, how come there is also power output produced in the biomethane upgrading case? Sorry, that is a confusing way of showing it. The biomethane upgrading consumes energy, it doesn't produce, but the facility needs to be supplied with energy, and then that needs to come from the grid. But yeah, sorry, it was not well illustrated. What's the respective biogas upgrading technology? Well, there are many technologies, and I didn't want to focus to them that much because overall, when talking about the facility of this size, we are like almost an order of a magnitude too low for most of the upgrading technologies to be actually commercially feasible. They become very attractive when we are in megawatt scale or multi-megawatt scale. And then there are many technologies, but I didn't want to go into those details. They all follow the similar path that low end is costly. What's the electric efficiency assumed for this SOFC solution? Well, SOFC technology is obviously actually a group of technologies. We also use different cells in our systems, and they offer different benefits, each and every one of them. In the DEMOSOFC, the sort of beginning of life efficiency was over 53 net from the fuel cell module. And then, as we know, efficiency decays over time as a result of degradation of the cells. But the average efficiency over the lifetime is nearly 50 in our calculations, at least. Some of our systems now with different types of cells actually have more than 60% net efficiency. What's the timeline for the cost reduction? Stack cost, total system cost should be down to or below 1,000 euros per kilowatt if 50-50 cost split between system and stack is maintained. Well, as mentioned, of course, there's some limiting rate of doubling of volume, but time is not the driver, volume is the driver that drives down the cost. There are well-known things such as choice of manufacturing techniques and buying in bulk materials and optimizing workflows when we go up in volumes. And then we assume also some learning curve effect that improves efficiency of production and brings down the cost. As highlighted by BEMI, it doesn't have to be below 2,000 euros a kilowatt, assuming 50-50. So 2,000 consisting of 1,000 for system and 1,000 for stacks. Of course, that is a long-term sort of a target level, or even below that, but when we talk about cost. But there are applications where already higher costs become commercially attractive, even without subsidies. Which size of a wastewater treatment or wastewater treatment plants has been used to evaluate the market potential? BEMI can answer. Yeah. There were different classes of size ranges.
Yeah, I'll take that question. Thank you, Thomas, and thanks to everyone for listening and coming up with such brilliant questions. So the minimum size of wastewater treatment plants we've taken is we've used the population equivalent. So all the plants in this study have a population equivalent of above 20,000. We've used 20,000 as a cutoff because we believe that generating biogas, having an anaerobic digester is probably economic in plants with a PE greater than 20,000. Of course, the methodology is robust enough to be applied to any plant sizes. So specifically to answer your question, we've taken a minimum population equivalent of 20,000, and the highest plant has a population equivalent of 1.1 million. So that's the range of the plants we've considered for the whole of Europe.
Okay. Yeah, I hope that clarifies it. Then is the interpretation about correct that the current cost of SOFC system is between 10,000 and 15,000 euros per kilowatt? It's not far from reality. Of course, when talking about the cost, you have to understand if it's a handmade individual demo unit or if it's actually produced in a production line. And there's a massive difference, and that relates to the following question: what is the major driver for the high soft cost? It's not complexity; it is lack of automation, lack of industrialization of manufacturing of the integrated hot process parts. So if you look at cells and stacks, and then the system, that they are very different in terms of manufacturing methods and materials needed. So the competencies and the kinds of investments that are required for industrialization of these two things are quite different. A cell stack consists of a high number of repeated units with very big potential of automating the process. And when automating, like with battery production or solar cell production or other similar production, automation not only brings down the cost, but it also improves the quality. When it comes to the hot process module manufacturing, which is highly integrated, welded and insulated structure, it's not rocket science, but it requires tooling, it requires sort of assembly lines and that kind of arrangements. So the cost is not so much in the components, but in the sort of overall labor that goes into producing either the system or some of its components that are not standard. But of course, yes, there's room for improvement in every area, like with industrializing any technical product. Okay, currently no questions in the other tool. I will inform if there are.
There is a new question. Have you seen it, Thomas?
Okay, yeah. Okay, now I see. Considering that the PEM fuel cells are more commercially available, do you have any estimation what the cost of developing a PEM FC system would be in the wastewater treatment application? No, I don't, and I don't quite grasp the idea why we would use PEM in such an application. Well, biogas, which is produced by anaerobic digestion, is quite an interesting sort of fit with SOFC, because SOFC is by its very nature fuel flexible. So we can use diluted biogas without removing the CO2. So it's the digester quality biogas is a mixture of methane and CO2 basically, and then impurities. And we don't have to remove the CO2, which simplifies everything and makes things much cheaper. Using this energetic embedded energy of biogas in a PEM fuel cell would require all kinds of things that cost money and consume energy and would not really produce as much energy as we can with an SOFC. Of course, PEM fuel cells, they have their benefits when you actually have hydrogen available. They're dynamic and they are cheaper by CapEx, but yeah, probably not for this application. The market size calculated to be in a market-driven situation is based on an assumption that the production of SOFC is solely used in wastewater treatment applications. If I have sales in other sectors, would the required market share in wastewater treatments reduce? Of course, what drives down the cost is the global volume, global demand. And for example, in our case, our modules are 50 to 60 kilowatt. We still use at least partly the same cells that are produced for different sized systems like micro CHP. So we generate, along with other manufacturers, we generate demand for cells that are also produced for other applications. And altogether, the global demand then brings down the cell manufacturing cost. Then wastewater treatment is, yeah.
I was just saying I was just going to add to what you're saying. Yes, the market size in the analysis was solely based on SOFC within the wastewater treatment plant applications. If the market is expanded to take into account all the sectors or other applications of the SOFC, the share required to trigger cost reduction, or the share required to occupy the market, will be lower, and the technology will get to occupy a bigger chunk of the market as the cost reduces. So in essence, the analysis, which is very much focused on wastewater treatment applications, is not an optimistic view of the SOFC. In reality, what we want to do is to use all the market segments in all the countries where the SOFC can be integrated. That way we can begin to see more accelerated cost reduction, taking into account policies from these markets, as well as how business models can be implemented in these markets.
Yes, this small or smallish scale biogas is an interesting early application for this technology, because locally produced non-commodity fuel is by its nature lower value, or sometimes even considered free. And if you think of the overall economics, cost of fuel is always an omnipresent and important factor in the total economics. If the fuel can, some fuel that would otherwise not be used or would would be used for low value applications. So it is of low value. If we can use that and produce a high value product, which is electricity at very good efficiency, then that improves the overall economics, even though the capex still remains somewhat higher than the competing technologies. What would be the cost of developing an SOFC system with the same size of DEMOSOFC at the moment? Well, DEMOSOFC is a project that started in 2015. We started developing the fuel cell module before that. So the module was more or less ready by the time the design was ready and in validation elsewhere. By the time the project started and the first unit was delivered in 2017. Since then, we have actually developed a follow-up version of the product. I showed the last sort of step along the pathway to commercialization, which we call C60. It is more integrated and more suited for serial and mass manufacturing, and it's there. So what would be the cost of developing? Well, this company and many others in the field of fuel cells is in the business of developing and improving these products, and of course there are development costs, but they are not limited to a particular application. Also the new product can use either biogas or natural gas as a fuel. It can be configured to use things like gas cleanup is different, but it's configurable. Any other questions? If not, I wish to thank all of you. Well, the team, DEMOSOFC team, of course, for putting things together, but also a very active and wide audience. It's been a pleasure to receive week after week such a good audience, and we'll be happy to tell you more. If you have any further questions, you can directly contact us.
Yeah, thank you to everybody. Thank you to Thomas and Benny for this presentation, and in general to all the speakers for these webinars. And yeah, we have your email contact, so we will keep you updated about the project, and you can, as Thomas said, write us for any further question.
Yeah,